In this video, we will look at how to write the channel expression for single input, multiple output, multiple input, single output, and multiple input, multiple output. Let us first consider the case of single input, multiple output. At the transmitter, we have single antenna, and at the receiver, we have multiple antennas defined by total. We have MR number of antennas at the receiver. So let Hi tau comma t represents the impulse response of the channel between the transmitter and the ith receive antenna. And the received signal at the ith receiver element is given by yit is equal to the channel impulse response convolved with the signal that is transmitted from the transmitter, that is S of t. And since we have MR links between the transmitter and the receiver, so this H channel, we can write it in the vector form. This is the channel impulse response corresponding to the first link, second link, and so on for the mth link. And for flat feeding scenario, we have seen that all the taus are equivalent. So we can skip tau in this equation when we talk about flat feeding, and simply we can write h of t is equal to h1t, h2t up to hmr of t. And since we have multiple receive antenna, so we will receive multiple signals yi at the receiver. And so received signal at the receiver can also be represented in the vector form, that is the signal received at first element, signal received at second element, and so on, signal received at mr element. And in the vector form, it can be written as y of t is equal to h of t, s of t plus n of t, where y of t is the vector, h of t is also a vector, s of t is a scalar since there is only one signal we are passing from the transmitter, and n of t is also a vector because at all the antenna elements we will separately add the noise. Now for the MISO case, when we have multiple antennas at the transmitter and single antenna at the receiver. This is just the reverse of the previous case, and here similarly we can also write hj tau t as the impulse response of the channel between the jth transmitter and the receiver. Similarly, we can write h of t is equal to h1t, h2t up to hmt of t. So in the previous case, h of t, this was the column vector, and in MISO case, this is row vector. And the different signal is transmitted from each of the antenna S1, S2, so on up to Sj. So then at the receiver, what we receive is the sum of all the signal that is coming from different channel. So then we can represent yt as the summation where j goes from 1 to empty because we have empty number of antennas, and from each of the antennas we are sending a signal s of j. So we have then s of jt convolved with the channel. So then we can write it in this form. And again, we can also represent this as in the vector form. We can write it as y of t, which is a single value because we have single receiver. We have multiple links, so h of t is a vector. S of t is also a vector because we are sending multiple signals from the transmitter, and n of t is a single value because we have only single antenna element, so there will be a single noise addition. Then this case can be thought of it like a downlink communication, where in the base station we have multiple antennas and at the receiver we have single antenna. And this SIMO case can be thought of like a uplink communication from mobile to base station, where mobile has a single antenna and base station has multiple antenna. Next we will go to MIMO, multiple input, multiple output. So here in the transmitter we have MT number of antenna elements, and at the receiver we have MR number of antenna elements, and correspondingly the signal that is transmitted from this, let's say this is the jth element, signal transmitted from the jth element will receive at each of the receiving antenna. So at the first element, receiving element, there will be a sum of all the signals that are transmitted from each of the antenna element at the transmitted side. And in this case, we have a channel matrix represented by H, which is of dimension MR cross MT. This represents the channel between the first link, of the transmitter to the first link of the receiver. Then this is first to the second, and so on. And then we have SJT, because we have multiple antennas at the transmitter, so we can transmit multiple antennas. So SJT is the transmitted signal from the jth transmitted antenna, and J goes from 1 to MT, which is equal to the number of elements at the transmitter. And similarly, YIT is the received signal at ith antenna element, where I goes from 1 to MR. MR is the number of antenna elements at the receiver. So at a single element, receiver element, YI of T, we will receive SJ, summation of all the copies that are transmitted from the transmitter. And in the vector form, we can write it as this: Y of T is equal to HT. HT is the matrix. YT is a vector because we have MR number of antenna elements at the receiver. So we will get MR number of signals. Then ST is also a vector because we are sending MT number of signals from the transmitter. And N is also a vector because we have MR receiving element, and every element will have a noise corresponding to it. So we can represent MIMO as Y of T is equal to H of T, S of T plus N. So this can be represented as MR cross 1. Let us draw this again. This is MT, and then at the receiver we have MR. So Y is MR cross 1 because at every element we are receiving the signal. So it is MR cross 1. This is MR cross MT because every element will have a link corresponding to it. Then the signal is MT cross 1 because we have MT number of transmitting elements and the signal is coming from each of the element, and the noise is MR cross 1. This is the generalized expression for multiple antennas. So this can be reduced to single input multiple output. Single input multiple output, we have M of T is equal to 1. We can substitute this MT is equal to 1 in this expression, and then we will get MR cross 1. So this is 1 now. So here we will have MR cross 1. So ST will be 1 cross 1. That is a single signal is transmitted in case of single input multiple output, and the noise it will remain the same, MR cross 1. Similarly, for the MISO case, we can substitute MR is equal to 1 in this case. So this will become 1 cross 1. So we have YT 1 cross 1. This will become 1 cross MT. So here we have 1 cross MT. This will be MT cross 1. So we have MT cross 1. and this is MR cross 1. Now we have one receiving element, so we will have only single noise, and this will be 1 cross 1, and we have NT here. So now we know how to write the expression for the MIMO channel, for the CMO channel, and for the MISO channel. And if you have the generalized expression of MIMO, you can also devise the CMO and MISO from it.